Hi, this is Peter with CalcBook, and today we're going to be doing just a short video talking about retaining wall overturning. So, quick recap, right? We are going to be using allowable stress design or ASD loading for our stability of the wall in overturning. So the first thing we're going to do is pick our point of rotation, right? For us, that's going to be in that lower left corner of the foundation. That's going to be the point at which this foundation wants to tip over to the left. We have our overturning forces, right, due to our lateral soil loading, so our surcharge, our active, our seismic, and then the corresponding moments due to their moment arms from the soil to the point of rotation. Then we have our resisting forces and moments, right? So that's going to be the weight of the footing, the weight of the stem, the weight of the soil over the heel, and the weight of the soil over the toe. And we do not use our passive pressure for overturning stability. So our problem statement for today, right, we have a retaining wall with a set of parameters here for the height of the wall and the soil and the thickness and all of that. We have a loading of 300 PSF surcharge, and then we're going to use the default soil properties given to us in CalcBook to determine the overturning stability. And if it's not working, we will make some adjustments to get it to be stable. So let's go ahead and open up CalcBook and we'll get started on the design. All right, we've got CalcBook open now. So we've already got all of our parameters inputted here for this retaining wall. So we have our demand already set at a live load surcharge of 300 PSF. And then our capacity, we didn't necessarily say we need to use the shear key, but we're going to include it. And then we also have an option here for including the heel side soil pressure on the shear key. So you'll see here these pressure diagrams extend it to the bottom of the shear key. If you toggle this off, they will stop at the bottom of the footing. This just has to depend on your jurisdiction or what reference you're using. Some require it, some don't. So just be sure to take a look at that about what you need to do for your retaining wall. So next we're going to go ahead and move on to the rest of our properties here just to confirm we have what we need. So our stem, right, we have a height of 12 feet, top thickness of 12 inches, bottom thickness of 18 inches. We won't worry about the rebar or anything else for our overturning. Our footing thickness is 2 feet, 24 inches, 2 feet of the toe, 5 feet over the heel. And then our soil properties, right, we just have a soil height of 11 feet on the heel, and then the rest of the properties we're going to leave as is. So you can see right before we get into it, we already have issues with all of our stability here. So our sliding, overturning bearing pressure for dead plus live, and our total bearing pressure, including seismic or wind. So let's just go ahead and filter this down to just our stability so we can just take a look at that. So first thing we want to do here is go into our demand for our overturning. So we want to go into the stability section and then our wall overturning demand. And here we'll have the loading for our overturning. So we have our factored lateral surcharge load, and all the factors for overturning are just 1.0 except for earthquake, which gets a 0.7. So we have 1.35 kips from our surcharge. We have our factored lateral soil loading for the active. So this triangular load here for the active of 3.64 kips, and then our seismic, which is an upside down triangle of 2.3 kips. And then we need to figure out the distances, right, the heights from the bottom of the footing to the centroid of that soil shape. So for our surcharge force, it's just a rectangle, so we just divide it by 2. Our active pressure is just going to be over 3, a third up. And then our seismic, since it's an inverted triangle, we take 2/3 of the height, and that's what we use for the force there, or for the distance, excuse me. From that, we calculate our overturning demand, right? So we just take our load times our distance for each of those different components, and we get a total overturning demand of 46.16 kip feet. Then we can go to the capacity side. So we go ahead and click into our stability, click into our overturning capacity, and we have a few things to calculate here. So first, we need to calculate all of our moment arm dimensions from that rotation point, right? So we look at our distance to the stem, we look at our distance to the entire footing for the weight of the footing, to the center of the footing, excuse me. And then we have the distance to the center of the toe side soil, and then the distance to the center of the heel side soil. Once we have all those distances, we can go ahead and multiply our weights that we calculated previously. We didn't show that, but those are calculated for all the vertical weights. So the weight of the stem times the distance, the weight of the footing times the distance, weight of the heel times the distance, and the weight of the toe soil times the distance. And from that gives us our factor of safety. And one thing to note about this factor of safety is that this already this does not have the factor of safety implied. So this is the pure factor of safety included here. So when you go to your soil properties, right, you'll notice that there is a factor of safety against sliding and a factor of safety against overturning. So the raw factor of safety here is 1.25, but our limit is 1.5. So we have set a factor of safety minimum of 1.5. That's why if we look at our DC ratio here, we are over capacity. So if we were to change our minimum factor of safety requirement to 1.0, right, this would go down to 0.8 because we already have a factor of safety of 1.25. So just keep that in mind, that this calculated factor of safety does not include the minimum requirements set by the user. So we'll go ahead and set that back to 1.5 because that's a pretty standard factor of safety requirement. And then we'll want to go ahead and update this calculation to see if we can get this to work. So let's go ahead and just look at our summary table here, and we'll go back, and I think the easiest thing to do is going to be to increase the heel dimension to get this thing to be a bit more stable. So we're just moving the resultant force closer to the center of the footing here by increasing this distance. And that should bring, many of these properties into spec. So there we go. We got our overturning less than 1, which is what we want. And we're not going to worry about the sliding and the other ones. That will be for a different video. But we do want to just make sure that our overturning is less than 1, which it is now. So that is how you do an overturning check for a retaining wall in CalcBook. We hope you enjoyed the video, and we'll see you next time.